This is Module 21 of Engineering Vibrations, an introduction to single degree of freedom systems. Today's learning outcome is to solve for the transient response solution of simple single degree of freedom systems that are experiencing undamped free vibration. Here's one example. We have a sphere labeled as C that's rolling without slipping back and forth on a cylindrical surface. And we want to put the transient response solution in phase angle form. So I'd like you to stop the video, think about what are you going to do first. It's always most difficult to determine how you're going to approach the problem. So once you've thought about that, come on back and we'll proceed. So the first thing you want to do is to choose a generalized coordinate to describe the system's motion. So again, I'd like you to pause the video and think about what generalized coordinate you would like to use. So I have chosen gamma, the rotation of the sphere, as the generalized coordinate. And here it is shown on the diagram. And so my next question to you is, what do you do next? And again, pause, and once you figure that out, come on back. What you should say is you want to go ahead and sketch the free body diagram equals kinetic diagram. And so here's my sphere. I'm going to show the system, the vibrating system, in its displaced position, and I'm going to assume small displacements. So on my free body diagram, which you should be very adept at doing now, right? You should be easy to do free body diagrams. You're going to have your weight term down, mg at the mass center. We're going to have a normal force up from the surface, and we're going to have a friction force so that the sphere can roll without slipping. And here is my kinetic diagram. This sphere is large enough that I'm not going to consider it a point mass, and so I've got the mass times acceleration in the tangential direction, which is mr gamma double dot, since gamma is our term. In this case, for my mass times acceleration normal, I've got mr theta dot squared, or mr omega squared. Again, this goes back to my earlier course on dynamics, engineering systems in motion, 2D dynamics, where our normal acceleration is based on this angle, theta dot, or this angular velocity, theta dot, and the distance from the rotation of the center of the sphere, which in this case is big R. And finally, we have the IC gamma double dot for the mass moment of inertia of the sphere times its angular acceleration. So those are my three kinetic vectors. What do you do after you have a good free body diagram equals kinetic diagram? Okay, as you've thought about that, the next thing to do is to come up with the equation of motion. In this case, I've chosen a point P at the location of where the sphere contacts the cylindrical surface, and I'm going to sum moments about that point P. I've chosen counterclockwise as positive for assembling my equation. That gets rid of the friction term and the normal force, since their lines of action go through that point P. I end up with mgr sine theta on the left-hand side, and on the right-hand side I have my IC gamma double dot minus my mass times acceleration tangential term times the moment arm from point P, which is R. So this is the result. I assume small angles, so sine theta becomes theta. And you could look up in a reference or online that the mass moment of inertia for a sphere with respect to an axis through its center normal to the plane is 2/5 mr squared. So I'll put that in. And with that, I'm getting closer to my differential equation of motion. I'm just going to collect some terms here. So what do I do next? Well, I've got Gamma is one of my terms, one of my coordinates. It's the coordinate I've chosen as the generalized coordinate, but now I've introduced theta, which is another angle, so I'm going to have to put theta in terms of gamma, and I'm going to have to use kinematics to do that. So I've got to find a relationship between gamma and theta. The velocity of the mass center can be expressed in terms of gamma from, in this case, for the rotating sphere, from this point up to this point, or you can express it in terms of theta, where you're rotating about this point up here, and it's theta dot times r, big R in this case. So little r gamma dot and big R theta dot both are an expression for the velocity of the center C. And so knowing that, I can rearrange that and say that, or I can actually choose as my initial conditions gamma and theta in some zero position and integrate, and I find that r gamma is equal to r theta, big R theta. And so theta becomes a function of gamma, little r gamma over r, and I can replace theta now in my equation of motion above. And so now everything's expressed in terms of gamma. And so the final equation of motion that I come up with is 7/5 m little r squared plus mg r squared over big R gamma equals 0. So a second order differential equation like we saw with the coordinates x or y, whatever coordinate I'm using. Let's put this in phase angle form, or what is the phase angle form of the response solution? Well, we know it takes this form. Now, instead of using x or y, it's now gamma. Gamma is our generalized coordinate, so it's gamma as a function of t. And instead of capital X as the amplitude of displacement, now I'm going to use capital gamma for the coordinate system, or the coordinate generalized coordinate gamma. And that's a cosine times cosine of the natural frequency times time minus the phase angle. The amplitude of displacement then, capital gamma, is a function of the initial conditions, gamma at time 0 and the gamma dot, or the angular velocity at time 0. And the phase angle is the tangent inverse, again, of the generalized coordinate gamma's velocity at time 0 divided by the natural frequency times the initial condition for the generalized coordinate gamma displacement. And so this is another example of a simple harmonic oscillator or simple harmonic motion, where omega natural now is the equivalent k over m. And you see it there. I can reduce it a little, and it becomes the square root of 5g over 7 big R. And that's our answer. Now, I've put in a couple of worksheets for you to do for practice, very similar to this. And I've also added the solutions in the modules so that you can see how you did as far as your work is concerned. Here's one worksheet. Then I also added another worksheet, and that should give you good practice for being able to solve for the transient response of single degree of freedom systems undergoing undamped free vibrations. And with that, I'll see you next time.